Hello and welcome back to Machine Learning. I'm Chivita Christie, and in this video, we are going to talk about recurrent neural networks. So let's begin. First, let's see what an RNN is. So RNN stands for a recurrent neural network, which is a type of neural network in which the output from the previous step is fed as an input to the current step. And in traditional neural networks, we know that all outputs and inputs are all independent of each other, which is not a good idea if you want to predict the next word in a sentence. So in this case, the previous words of the sentence do matter a lot. And if you wanted to do any such thing, you might want to use a recurrent neural network. So we need to remember the previous word to generate the next word. So traditional neural networks are not efficient for any of these NLP applications. NLP means natural language processing applications. And RNNs also have a hidden stage which is used to capture information about a sentence. So there is a hidden stage in between. And they also have a memory. This memory can be used to capture information about the calculations that are made so far about the sentence. So in theory, RNNs can be used can use the information which is there in arbitrarily long sequences, but practically they are limited to look back only a few steps, okay, because there is a memory, but they cannot, just look back a lot of steps. They can look back certain number of steps. So, for example, if you had a sentence of 15 words, they could probably look back up to information about the last 4 words, but not all the 15 words that have been encountered so far. So here we have a small diagram showing the architecture of an RNN. You can see this is the network, and here you have XT. Wherever you can see XT, this X over here, all these are inputs at time t. ST stands for the hidden state at time t, which is right here. And OT stands for the output at time t. So this is the output you can see. Okay. So we know that the neurons in the output layer depend on how many outputs you have, how many types of outputs you have. So you could have that many types of outputs. These are all inputs. Whatever you see in the middle is the hidden layer. And all of these things here, they are all weights that are applied to all the neurons. Okay. So what does the word unfolding mean? So unfolding means writing the network for the complete sequence. For example, if you have a sequence that has 4 words, then the neural network will be unfolded into 4-layered neural network. Okay, so it's not necessary that you have to decide how many layers should be there, but it depends on the sentence you pass. Okay, depending on how big your sentence is, you will have that many layers in your neural network. It will get unfolded into that many layers. And you can think of ST, which we saw, think of that as the memory of the network, which captures information about what happened in all the previous steps. So we know there's a hidden layer in between. So it can be, more than one hidden layers. So if you have a lot of hidden layers, then all those hidden layers, they capture information about what happened in the previous steps. And if you have a traditional neural network, then it uses different parameters at each layer. But in RNN, it shares the same parameters across all the layers. So in the diagram, we could see that there are the same parameters U, V, and W, which are being used across all of the layers, right? So we are not using any new parameters. We're using the same U, V, W parameters through all the layers of the neural network. And using the same parameters across all layers shows that we are performing the same task with different inputs. So we are reducing the total number of parameters to learn, okay? So performing the same task with different inputs would reduce the total number of parameters that you require to learn. And the tree set of parameters u, v, and w is used to apply linear transformation over their respective inputs. So the parameter u transformation, the input xt to a state st, right? Because x is input, st is the hidden state. So u is used to transform xt into st. W transforms a previous state of whatever st minus 1 was to the current state st, because depending on how many hidden layers you have, that would be, you will have that many STs, different ST states. And the parameter V is going to map the computed internal state ST to the output OT. Let's take a look at the formula to calculate the current state. It is HT equal to F of HT minus 1, comma, XT. Okay, so this is my current state. It requires information about the previous state as well as the input to find the current state. So HT is the current state, HT minus 1 is the previous state, and XT is the current input. And the equation that you apply after activation function tan H is like this. HT is equal to tan H, WHH, HT minus 1 plus WXH, XT. What does that mean? You have WHH, which is the weight at the recurrent neuron. WXH is the weight at the input neuron. Okay, so WHH is basically the weight at whatever layer you are at for that neuron, and WXH is whatever was the weight while doing the input. And once you calculated that, then you would want to calculate the final state, which means the output, which can be calculated like this. So you have OT equal to WHY into HT. And here OT is the output state. Okay. Y is the output state because the weight at output layer is HT, right? So weight at the output layer is WHY. Okay. So WHY is the weight at output layer, OT is the output state, and HT is the current state. So that's how these equations work for RNNs. Let's now talk about different types of RNN architectures. So the common architectures which are used for sequence learning are one-to-one, one-to-many, many-to-one, and many-to-many. Let's see one-to-one. So in this model is very similar to a single layer neural network, as it only provides you with linear predictions. And it mostly uses fixed size input X and fixed size output Y, because there's only one layer. So if you were processing sentences, then you would have to use basically sentences with one word. So you could just, process words, not a full sentence. Okay. So you could do image classification with this because you can have a single image that you want to process. This is what it looks like. So you have X. These are all the neurons in the hidden layer, and then you give out Y as the input. The next architecture is one-to-many. So this consists of a single input X, activation A, and multiple outputs Y. So once again, the input is only one. There is only one activation function, but there are multiple outputs. So if you had to generate an audio stream, then you might want to use a one-to-many function because you have one input, but for the streaming purpose, you might want to have outputs in several formats. So it takes a single audio stream, but generates new tones or new music based on that stream, and that's why there are many outputs. So in some cases, it propagates the output Y to the next RNN units. So this is what a one-to-many looks like. So you have, this is our X, this is our hidden layer, this is one output, And then this output is passed as the input to the next unit, which produces another output, and so on till you get your final output. And everywhere there is an activation function A involved. The next architecture is the many-to-one architecture. So this consists of multiple inputs X, such as words or sentences. There's also an activation function A, and it produces a single output Y at the end. So multiple inputs, but one single output. This type of architecture is mostly used to perform sentiment analysis as it processes the entire input, which means collection of words and sentences, to produce a single output, which is, either what kind of sentiment it is, positive, negative, or neutral state sentiment. So sentiment analysis is where you analyze different texts and you try to find out what is the sentiment behind them. So you could essentially have a text of 10 lines, but you could analyze it and just say that this particular text is positive or negative or neutral about some particular product or service. Okay. So it could help you to analyze how your company is doing, how your products are doing. And so to do all of that, um, you could use a many-to-one architecture because it takes as an input several words or sentences, and then as an output, it generates just one thing, one result, which can be either positive, negative, or neutral. This is what a many-to-one neural network looks like, RNN looks like. So you have, once again, X over here, Y over here, and it's fairly simple. You have multiple inputs, and you have actually only one single output in this case as well. And everywhere you have different weights. These are all hidden layers which generate different weights. So this is a recurrent neural network, which is of many-to-one type. The next one is a many-to-many type network, which is a single frame. In this, you have a single frame as an input for each RNN unit. And what does a frame represent? It represents in multiple inputs X, activations A, which are all propagated through the network to produce an output Y, which are the classification result for each frame. Okay. And this kind of network is mostly used in video classification, where we try to classify each frame of the video, because one video contains, a video is basically nothing but a kind of a collection of images that are moving very quickly. So if you had to classify each and every frame or image within that video, then you could use a many-to-many network, because you have many frames of images coming in and you want to perform classifications, which could be into many different classes. So you would have many neurons in your input layer and many neurons in your output layer, which means it is a many-to-many function. So once again, basically the diagram is more or less the same as what we saw previously. Everything is connected with all the outputs here. All inputs are connected with all outputs. Okay, and there are hidden layers, which can be any number of hidden layers you like. We also have something called bidirectional RNNs. So in this neural network, there are two hidden layers which are running in opposite directions, and they are connected to produce a single output. And these layers, they allow the neural network to receive information not just from the past, but from the future as well. So for example, if you have a word sequence, I like programming, then the forward layer will input the sequence as it is, but the backward layer will feed the sequence in a reverse order. So it will be like programming like I. And if you do this, then your neural network is going to get information from the past as well as future state. And the output of this will be calculated by concatenating the word sequence at each time step and generating the different weights. So here is a diagram showing that. These are all the inputs. Those are all the outputs. This is backward layer. Okay, this is the forward layer. So the forward layer essentially moves in forward direction, backward moves in backward direction. And the input from the backward layer is given to the input layer. The output from the backward layer is given to the input layer. Output from the forward layer is given to the um, output layer. So essentially, the output layer has information about the past, and the input layer has information about the future, which helps in making our recurrent neural network better. Now, to conclude this video, let's take a look at some of the applications of RNNs. Number one is text summarization, which means you want to create a small summary or conclusion of a big text. Like you could have something from literature, a big poem or a big story, okay, and a news website wants to display that in a brief way. Okay, so from each and every news article, maybe you want to generate a short summary to display on your website, then text summarization would be useful. There's also text recommendation, which is like, text autofill or sentence generation in the data, which can all be done using RNNs. So when you're typing something and you are getting prompted about what the next word should be, that is text recommendation. There is also image recognition. So RNNs can be combined with CNN in order to recognize an image and also give its description. And you could also use them in music generation because RNNs can generate new music or tunes by feeding a single tune as an input. And it could just find new notes or tunes that can get along very well with the input that you provided. So that's it for this video. Thank you for watching.